In our last section, we looked at how to find the pH of a strong acid, and that was pretty easy, pretty straightforward. Now we're going to see how to find the pH of a weak acid. It uses the same concepts, it just has a little extra step built into it. The reason why it has that little extra step is because remember that weak acids do not completely dissociate in water. They're weak electrolytes. They only make a few ions. Alright, the equilibrium lies to the left in these guys. They only partially ionize. However you want to say it, it means pretty much the same thing. We don't make a lot of ions out of this. So that when the reaction is done, you're going to have a lot of that original acid still left over. You're going to have a little bit of ions that are formed from that acid. So our weak acids we need to know. Most of these you already know. You know phosphoric, carbonic, acetic. Another one to add to our list though, hydrofluoric. These are all guys that only partially dissociate. Now the equilibrium expression for the dissociation of any acid into water is going to look pretty much like this little equation right here. Alright, but this doesn't have to just be for HCl. It could be for any acid, so I'm just going to change this Cl to an A. So this is just HA now, alright? Making some sort of A anion here. Now, if you have a really strong acid, it's going to make a lot of those ions, so that means that you have a pretty large value for Ka. If you have a real weak acid, it's not going to make very many ions. You're going to have a small value for Ka. So you can use the Ka value to tell you the relative strength of the acid. If it's big, strong acid. If it's small, weak acid. Now for our strongest acids like HCl, H2SO4, HNO3, your equilibrium lies so far to the right that there is no way to really measure the amount of HCl that's left over. And so you can't really get a good measurement of Ka. And so for what you may see for values of Ka for HCl or whatever, you may just see rounded numbers, or you may see numbers that say greater than such and such, and this is the reason why. Now over and over and over again you're going to see this, having to calculate the value of Ka from pH, or use your Ka to calculate your pH, vice versa. You have to go back and forth. Alright, the way you're going to do this is you're going to do this just like we did back in chapter 15, using Ka to figure out our values in our ice table, or using our ice table to figure out our value for Ka. So we're going to write a balanced chemical equation. We're going to write an equilibrium expression, alright, we know all this stuff, and we're going to list our initial concentrations, we're going to list our change, and we're going to find our equilibrium concentrations. Now usually our change is going to end up being X, and so our equilibrium is also going to be done in terms of X. We've seen that before. And then we substitute that into our equilibrium constant. We substitute those into our equilibrium expression, and we can use that to solve for our value for X. Now one thing that's really important that we haven't done before is this right here. And when dealing with weak acids and weak bases, remember that you don't make a whole lot of these ions, and that means that the change is not going to be that big. And that means that if you have an initial concentration of a certain amount, but it changes by a very small amount, so you have an initial concentration of 0.1 molar, and it only changes by 1 times 10 to the negative 6th molar, then that's pretty much still equal to 0.1 molar. It doesn't change it very much at all. And so this little guy right here, we're assuming that the concentration of that substance minus the change is still equal to the concentration of that substance. This is only valid for very small values of K. You cannot use it when the values get too big. So how do you know when it's too high or too low? You use something that's called the 5% rule, which I'm going to show you how to do later on. Then, once you figure out what X is, you can calculate hydrogen concentration, you can calculate your value of pH, and usually that's pretty good. That'll get you all the way through the problem. Now, every now and then you may have a problem where you have a mixture of weak acids. Whichever one has the highest Ka value is the important one. Or you may have a polyprotic acid. Same sort of thing happens there. Alright, so here's an example problem. We've got formic acid. Gives us the pH, it gives us the molarity of it. It wants us to calculate the value for Ka and find the percentage of the acid that is being ionized in the solution. So again, first thing we're doing is we're writing a chemical equation. Okay, after we write our equilibrium expression, after we write an equation, we're gonna write our equilibrium expression. Alright, so I got this far. And a lot of times I'll set up my ice table first, but it's already given me the pH. And since it already gave me the pH, I can actually use that to go ahead and solve for the concentration of hydrogen ions. So I think I'm going to go ahead and do that first. And here I get about 4.2 times 10 to the negative 3. Now again, try putting this in your calculator yourself. Make sure that you can solve these types of problems. Alright, so I got concentration of hydrogen ion. Now I can go ahead and work on my ice table. It tells me in the problem that the concentration of the solution was 0.1 molar. When it gives it to you like that, that's always the initial concentration of your original aqueous solution. And your original amount of your hydrogen ion and your anion are both going to be 0. Alright, now what we found here is we found the equilibrium value of hydrogen ion. So that number is going to go down here. And according to this equation, this hydrogen ion and my anion are going to be made in a 1-to-1 ratio, so they're going to be the same number. And then your equilibrium value for the HCHO2 is going to be equal to 0.1 molar minus that 4.2 times 10 to the negative third. I'm going to just write that real small there. And you know what? 0.1 molar minus 4.2 times 10 to the negative third is pretty darn close to 0.1 molar. So I'm just going to leave this 0.1 molar because it's pretty darn easy to do that. Now once I have my equilibrium values, I can plug them into my equilibrium expression. And when I do that, I get a K value of 1.8 times 10 to the negative fourth. Now to figure out the last bit of this question, what percentage of the acid has ionized? Well, I started out with 0.1 molar solution. It had ionized to a 4.2 times 10 to the negative third moles. And so I just take that percentage. I'm going to move this over here so y'all can see this because I'm out of room. And if I do this, I see this ionized about 4.2%. Now, a little bit ago, I told you about the 5% rule. It was back here, right here. And I said you could use the 5% rule to figure out whether that approximation is valid to use. Alright, like I used this 0.1 right here is equal to about 0.1. I can check that by doing this right here. If this is less than 5%, then it was perfectly fine for me to use that approximation. If it's greater than 5%, then that was too much of a round, and I need to go back and I need to calculate it exactly. Most of the time, you're going to be fine to do this. Every now and then, though, it's too much of an adjustment, and it messes your answer up too much. Alright, so now we're going to do the opposite of what we just did. We're going to calculate the pH, and it gives us the Ka. You start out exactly the same. You do balanced chemical equation. You do your equilibrium expression. So let's do those two things. Okay, so here's our equation. Here's our equilibrium expression. Now, it doesn't give me pH, so I can't do what I did before. But it does give me the initial value of the HCN. It's 0.2 molar. And it gives me the value of Ka. So what that means is I can do something like this. I know this is 0.2 molar, this is 0, this is 0. This is going to go down by x, this will go up by the same, this will go up by the same. So that my equilibrium values of H plus and C and negative are both going to be x. My equilibrium value of HCN is going to be 0.2 minus x, which since this Ka is really, really, really low, this is going to be equal to 0.2. Almost exactly. Now that I have that, I can plug this into my equilibrium expression. So let's go ahead and try this. So here's what this would look like with all my equilibrium values plugged into my equilibrium expression. And then I would just go through and solve for x. Now I've got this value for x, which is equal to the concentration of my hydrogen ions, right back here. And so that means that I can now use my pH equation to solve for pH. And this is going to give us a pH of right around 5. Now again, when you do something like this, stop and ask yourself, is that a reasonable pH for a weak acid? Oh yeah, it is. That is a very reasonable pH for weak acid. Now I didn't even bother to do the 5% rule on this one because I knew that this was going to be way less than 5%. But if I did, I would want to take the amount it dissociated by divided by the original amount and multiply it by 100, make sure that it's less than 5%.